This was the question I was asked to answer, and I think you can probably guess my answer is yes. And I've shown a picture of an engineer from EQUINOR, and I'm very keen to emphasize the well technology element of this activity. But let's see it a little bit in context. This is the beautiful cave paintings at Lascaux in the Dordogne area. I want you to notice a couple of things about this. It's Paleolithic. It's quite beautiful. I think Picasso, Monet would have been impressed. So I would say Paleolithic man was sentient, nearly as intelligent as we are, and certainly interested in the arts. The second thing is you can see there's a lot of black pigment, and they used soot as a black pigment. So we know it was a wood-based society, and they certainly had a wood-gathering industry at that point. The third thing is that they were hunting animals, primarily a hunter-gatherer society, and the main animal depicted there is the auroch. Anyone seen one of those? Now extinct species. It's the wild bovine species which is the ancestor of modern cattle. We know that human beings killed off that species because the last surviving member of the species was 1600 in Poland. So it also reminds us of the devastating impact of humankind on our biosphere and our planet. And in fact, as a geologist, I can see in the recent geological record the evidence of the burning of the forests of Northern Europe, where I've seen them. But pretty much throughout our planet, we burnt forest as we entered the glaciation period, post-glacial period. So that's the cave paintings. I'm going to add my own graffiti to the cave paintings. So there's the Vostok ice core record of atmospheric CO2 concentration, which I think most of you are familiar with, showing the oscillation in CO2 concentration between the glaciation periods and the post-glacial, interglacial periods. And that's fluctuated within a range which we know is sort of, if you like, a geological precedent. And then the top part of the curve, of course, is the Mauna Loa recent data set, which takes us way up past 400 ppm. And you all know this story, but I want you to put it in a different context. So the Lascaux cave paintings, 17,000 years ago, those humans were just at the end of the Ice Age, in the early part of the interglacial. CO2 levels significantly lower, okay? And we've been living through that interglacial period, and we've probably postponed the next glaciation with our current activities. And what will happen next is full collapse of human civilization if we carry on the business as usual path. But of course, we all know that story, and we want to avoid the collapse of human civilization. And one of the reasons why I'm stressing this is that we have to change the debate of why we're wanting clean energy. And my main argument to my petroleum engineer colleagues, to students, to members of the public, is that this is human-scale civilization issue. This is one of the biggest issues of mankind, and you've heard this many times, but I think it's helpful to put it in the history of mankind. So I'm now going to move on to, what we've done in the modern age. So as many people have alluded to here, we've been through the Industrial Revolution, which was dominantly coal-based, and then we moved into the petroleum age, which is where I am. I'm part of the petroleum age. I'm a provider of oil and gas in the petroleum age. And the scale is metric carbons into the atmosphere, so you multiply by 3.5 to get 3.7 to get the CO2 volume fraction. So it's a well-known, documented industrial activity of throwing CO2 into the atmosphere. What happens in the future? This is my sort of very simplistic perspective of acceleration or deceleration rates into the future. Our business as usual scenario was just continuing to increase, so we're on an accelerating trend of CO2 into the atmosphere. And in the last few years, there was hope that we could reach the orange dotted line, which would be constant CO2 emissions to atmosphere. But we haven't actually managed that. So currently, we're just a little bit above the orange line. We still haven't managed to reduce the acceleration rate. And of course, the demand is to decelerate dramatically. And when you hear about the 1.5 degree scenario, 2 degree scenarios, we have to be well at that blue line to achieve 2 degree scenario. So the deceleration is substantial. And again, most of you know that. But what I'm going to try and do is say no more about the problem, but much more about the solution. So we know that human society will require rapid growth in renewable energy. They will need dramatic improvements in energy efficiency, and those messages have been communicated already at this conference. And they will need rapid decarbonisation of energy, industry, and food. And I'm quite keen to focus on not just energy, industry, food supply. So the societal needs are well understood, and they're very heavy, okay? And then on the other side of the seesaw is industry trying to meet that challenge. And I do think, and this is a debate we've had much today, is it government or industry? Well, ultimately, I do think it's the industry that will deliver the solution. Government can create the policy, but we must have industry delivering. And yes, I'm going to say that some kind of modified oil and gas industry is most likely to deliver the solution. And there are very specific reasons why they're likely to be able to do that. They're used to large investments and long-term projects. And if you look at decarbonisation, they are substantial efforts that are needed. And oil industry have a long history of that, but I always say modified oil industry. It'll be some kind of energy business that does this. We need a lot of CO2 management and disposal at industrial scales, and I will show you how that works. And we also need subsurface resource management skills and tools, and many people, including our radioactive waste disposal friends, have stressed that. We need those skills to be able to manage this decarbonisation profile. And then the third member of my lovely picture here is the yappy dog. And he's really got the key to the solution. Because I do think we can balance the industrial challenge against society's needs. I think we can definitely do that. But the problem time and time again, and has been in the UK, is the yappy dog. It is the public-private partnerships which are absent and the societal and political engagement in this problem. And it is repeatedly absent. You know, and school children, enthusiasts, NGOs, we're all frustrated at the lack of progress. And why is it? I mean, I would contend we understand the societal needs and we have the solution, we're just not deploying it. It is, if you like, an advantage to work in Norway, where I've spent my last 20 years of my career. Norway has it's a very oil-dominated society, but has a very progressive attitude to that resource, and has imposed a CO2 emissions tax way back in 1991. And so we have a long track record of operational experience of carbon capture and storage. And this SNOWIT project, which I've worked on a lot, is in a way an archetypal, typical project of what we want to be able to do, where we take an industrial capture source onshore and we pipe the CO2 offshore and dispose of it offshore. There's lots of reasons why I think offshore storage is more likely to happen than onshore storage. It's quite a large project. The capacity is huge. The investments are huge. I don't remember the capital investment number, but we are talking about billions of US pounds in this investment. It's CO2 capture allied with a LNG plant onshore, and the offshore disposal is 2 CO2 injection wells also allied with the gas production well system. So there's a lot of economies of scale and utility of the oil and gas infrastructure in achieving the cost-effective capture and storage solution. And very briefly on the technology, one of the things that our experience at SNOWIT has told us, it wasn't as easy as the Sleipner project, which has been running for even longer. Here the permeability was a bit lower and the geological challenges were a bit more tricky. And what we had experienced in the first few years of operation was a gradually rising pressure trend towards the fracture gradient, which was undesirable. So the vertical line is where we changed our injection plan, we did a well intervention, and then we injected into a new formation, and we had the dropping off pressure profile. And this project continues to deliver capture and storage very successfully, and it had early operational challenges which we solved. And in fact, if you looked at all of the CO2 operations we have been involved in, all of them have had operational challenges. It is normal when you drill a well and inject CO2 underground to have some challenges, but they're easily surmountable and you find ways of working around it. And what we show in this project is how having a flexible well solution and using monitoring, you can, if you like, handle the geological uncertainties in the subsurface. Currently, many of the players in the Norwegian continental shelf, and this is a partnership between EQUINOR, Shell, and Total, are working on the next generation full-scale demonstration project, which will be doing the same thing, taking onshore capture around the Oslo area, actually shipping it around to the west coast of Norway, and disposing of the CO2 in a project which, on the face of it, looks very similar to Snøhvit in concept, but in this case, we'll have intermediate storage on a coastal landfall point on the west coast of Norway. And we're actually saying to our European partners, we're willing to take additional volumes from any other European country into this facility. So we're actually inviting you to dispose of your waste CO2 products in our facility. Obviously, there's an economic discussion to be had as well. How much are we going to charge you for that? But the overall concept, and again, if you look at the Norwegian government, 5 million people in a very wealthy state, which historically has depended on fossil energy for its wealth, is saying, we're doing this to stimulate change globally. We want this project to stimulate this behavior globally, and we want other nations to use this facility. So it's very much a contribution to the global decarbonisation. And there is an argument that if we gradually reduce the risks of these early projects, we should enable further storage projects to happen. We hope to see stepwise developments, and we really do hope the UK will be having its own CCS projects in the same basin. And it should be a basis for an emerging set of value chains. And yesterday you heard about our hydrogen project, and there's also potential for CO2 enhanced oil recovery should those projects have enough CO2. So we're thinking the Norway CO2 storage hub could be a catalyst for rollout of CCS in Europe and could make significant differences. So how much CO2? So this is a track record of what CO2 we have stored in the subsurface. And you can see Sleipner and Snøhvit in there. So it's the cumulative CO2 stored. And right now, by just the end of 2018, we've passed, 24 million tons in the subsurface, okay? And our current rate of storage is about 1.3. The capacity at Snøhvit is 0.8. The capacity at Sleipner is a little bit more than 1. But the actual storage, of course, is the number here. So we've gradually moved from an annual rate of 1 to 1.3 million tons. And as we bring in the next project, which is the Stripey line, we should get to 2 million tons per annum. Okay, so it's significant, but I'm going to ask you how significant. And here's a little bit of the public communication of this issue. So how much is 1 million tons of CO2? And I think a lot of people in the room can answer that question. Well, it's the annual emissions of 300,000 cars. Okay? Of course, emissions per car is going down. So a modern low-emissions car, it would be even more. It's about 5 million passenger kilometers of air travel. And it's about 100 million tons per kilometer of maritime shipping with conventional diesel shipping. Okay? And it's 1/10 of Norwegian road traffic. And I want to emphasize to you today, that's one well. One CO2 injector at Sleipner is doing all of that. Just think of the efficiency of that process, okay? One well gives you 1/10 of Norwegian traffic. 10 wells gives you all of Norwegian traffic emission. Now, obviously, at the moment, at the same time, we're electrifying our transport, so we probably only need 3 or 4 wells to do all of Norwegian emissions if we think to the future. So it's substantial, the capacity of one well. And then another question I had, especially with the hydrogen project, I got asked the question many times, well, can you really dispose of 20 million tons per annum, or 17, which was the design capacity of the hydrogen project? Can we scale up from 1 to 2 to 10 to 20? Well, another very simple mass balance. Currently, offshore Norway, in our operated fields, we're injecting 35 billion standard cubic meters of natural gas as enhanced oil recovery, okay? There's numerous wells doing that, and we've been doing it for decades. If you just do a mass conservation of that volume of methane to CO2, we're already injecting 65 million tons of CO2. Now, obviously, we're not, and I'm not suggesting we can convert those wells automatically to CO2. I'm just illustrating that the dimensions of the problem are very manageable. If we had had a CO2 injection policy in the Norwegian continental shelf, we could have been doing it at the 10 million tons per annum scale. But what we have had in the offshore Norwegian sector is government policy to stop flaring. So therefore, the operators inject gas into the oil fields. So it's coupled with policy, but it's very doable. Henrik Andersen talked about the full value chain H21 project, and I was involved in the storage part, so I'll just restate, if you like, how we're handling the storage part of the Hydrogen 21 Vision project, which is a substantial delivery of clean energy to the UK, heating, potentially power sector. We're thinking of using 3 bunter sandstone structures. So we've dimensioned the injection demand to say, well, how many geological structures would we need? Of order 3. We think we could do that development with 12 subsea wells from 4 templates. So we need kind of templates spread over each structure, and then a well pad into each structure. And you know, that's with fairly constant rates. So the actual number in the future might be a little bit different from that, but it's of that order. And we've had to look at the baseload seasonal fluctuations. And you can see also with this sketch, which is based on both the Snøhvit project and the Northern Lights Norwegian project, that we're using the same concept all the time. An onshore plant, compression onshore, it's dense phase CO2 in the pipeline, into the wellhead and into the subsurface. So it's technology that we've used many times before. This is the load diagram for the H21 project, showing in the colors how we would use the 3 structures to handle the seasonal fluctuations. And it is quite demanding. With the winter load versus the summer load, we'd essentially need 1 structure devoted to fluctuations between the winter and summer seasons. And the details of that handling of well rates and whether you'd shut them in or whether you'd just run them at a lower rate, we would probably work out in the next phase of the project. But again, it's doable, and the argument to the hydrogen project is we could absolutely handle of order 20 million tons annual storage. So in the remaining part of the talk, I just want to talk a little bit about another aspect of the oil industry, which is the pressure management story. So this is going a little bit back into the last 100 years of the petroleum industry. So you probably remember the idea of oil gushes. Early California, shallow oil drilling. You drilled down to a formation and the oil burst out, and then you had to control the pressure. That doesn't happen now, hopefully. So, but roughly speaking, what was the case was that a hydrocarbon resource in the subsurface had buoyancy pressure, and if you intersected that structure, there was an artesian type of effect. Over the last 50 years, we've developed more and more pressure management solutions. We have water gas injection, we have balanced drilling, and we manage that pressure in a way to optimize the recovery of the reserves. So that's a well-known history. What happens with storage? Well, we will also need a form of pressure management. And we like to talk about this as repressurization theory, okay? So by and large, most formations are going to be at the hydrostatic pressure, and you can take them up to the fracture pressure, which is the orange line. And some oil fields are starting at a higher than hydrostatic pressure. It's quite a complex story. But ultimately, we have that space between the hydrostatic pressure and the fracture pressure to manage our storage in. And another little subtlety is that some oil fields have been depressurized below the hydrostatic pressure. So there is also a class of storage situations where you depressurize and then repressure. So we're going to go a little bit through those situations with some simple examples. The first one is very similar to what we observed at Snøhvit, a sort of gradually rising pressure up to some limit, and then we change the injection plan. And that is a normal case, is that as you inject a fluid or CO2 into a formation, the pressure would rise due to some constraint and a far field constraint, and eventually you'd come to a stop pressure. So that is, if you like, a pressure-constrained injection case. That is the case for Snøhvit. It is not the case for Sleipner, which has very little pressure limitation. So not all injection cases are like this. And to achieve that, you need to understand all those things: fracture pressure, mechanics of the system, what are the acceptable pressure limits, and how would you monitor the development. There's another case which we've looked at more recently, was what about the pressure depletion case? And there are a lot of oil fields that have depressurized or are continuing to depressurize. And what we've become increasingly aware of, if you start injecting CO2 in a pressure depletion case, you can eventually get to the point into the future where the CO2 moves into the gas phase, which is undesirable for lots of reasons. Poorer capacity, also harder to manage where the CO2 will go. And I'll show you a case there, because what we found with the current Northern Light Norwegian CCS project is that we are planning to store in the vicinity of the Troll gas field, which will continue to deplete, has already depleted and will continue to deplete for 50 years. And there's three model scenarios in here. If I show you the central case, and here we are looking at large-scale storage for the future. So in the central case, we've injected 600 million tons of CO2 into a multi-well, two-structure completion. And this is showing you the case well into the future, 650 years into the future. And then with no depressurization in the central case, we have CO2 constrained to our two structures, and that's an acceptable situation. But if we switch to reality on the left-hand side, which is the effects of depressurization of the Troll gas field to the northwest of where we're injecting, then we get this plume expansion into the future, which is very undesirable, and we would get spilling of the CO2 to the east there. So we want to avoid that. And then what we did in the middle is said, well, could we inject enough CO2 to compensate the pressure depletion effect? And sure, you can, but it's a lot of CO2. So here is 3 gigatons of CO2 in the same time frame, which actually compensates that depletion from oil and gas, but gives you enormous capacity. So it's a play between pressures, how you would actually achieve large-scale CO2 storage. And the final little piece of the puzzle I want to alert you to is the monitoring story. Since we have a lot of experience with operations in EQUINOR in Norway, which is very beneficial to the worldwide community, we also know what it's like to be an operator. And you are constantly under scrutiny because people are worried about the project. Is it going well? Does it leak? Has it got problems? So there's a big burden on monitoring. And last autumn, we presented a paper at the GHGT on an advanced monitoring solution. And I do think for safe storage, for convincing safe storage, we're going to need good monitoring because it's going to be very much in the public eye. And we've shown how using next generation monitoring, both marine seismic streamer, seabed detection, fiber optic solutions, optimized monitoring strategies for the environmental monitoring, and quite a lot of digital analysis, we can do that very effectively. And then the question is, well, is it cost effective? Can you afford all that monitoring? Hard to answer cost questions. So to address the cost question, we said, let's take the history of Sleipner and Snøhvit and create a reference case, which is not exactly what we did, because we can't share that data for commercial reasons. But what we've done is here we've created a generic reference case for the cost for an offshore Norwegian program, essentially as we did for Sleipner and Snøhvit, projected into the future. And it turns out that our reference case monitoring cost is 42 million euro, which is a nice number. It's converted from Norwegian kroner at 2015 prices to euros, but it turns out to be Douglas Adams' magic number. Good to remember. And if you do it per storage ton, it's 2 euros per ton. Now I ask you, if I'm going to store your waste products of CO2, don't you think 2 euros per ton is good value for money? I would say it's extremely good value for money. But we do have a challenge because people say, well, why spend all this money on seismic acquisition, which is not cheap? And the key storage costs, ultimately, are drilling wells. And in the offshore domain, 50 to 100 million euro per well is a typical cost range. And a major well intervention, about 10 million euros. Okay? So those are your cost items. And our main argument is that monitoring doesn't cost a penny because you're avoiding significant capital items. So if you can demonstrate that your monitoring program at 2 euros per ton actually avoids additional well costs or unplanned intervention costs, then you've really got value for money. So we're trying to talk up the positive value of monitoring. I would have to say against stakeholders who don't want to spend very much on monitoring. There's one of the challenges. Okay, conclusion slide. I think we all agree we urgently need to decarbonize energy, industry, and food. I would argue that some kind of modified oil and gas industry is ideally suited to doing that. We have the skills, we have the tools. I've shown you that CO2 storage in saline aquifers has enormous potential. One slight injection well is equivalent to the emissions of 100 million tons of maritime shipping. Large-scale CCS will need some kind of basin-scale pressure management, and certainly understanding those pressure limits is going to be important, and we could potentially use oil field pressure depletion history to give us added benefits. And as we know, CCS is a large ticket item. We need to talk up the societal value. The value of these CCS projects is enormous. The cost of avoided emissions per pound, dollar, choose your currency, I would say is really good value for money. If you look at the cost of society, and the Stern report has made the similar claim many times over. And well, we're ready to move forward. And it's really a question of this government willingness to put in the policy and an industrial willingness to deploy. So thanks very much.
Okay, a couple of quick questions for Philip. Jonathan, can you, when you ask your question, say who you are and speak into the microphone? Thanks.
Jonathan Turner. Can I just check, Philip, the implications of monitoring is that if you did find leakage, then you could essentially go through a sort of retrievability or reverse engineering process. Is that correct?
Yeah, I mean, we've shown that you could stop injection. We've also shown that most likely the leakage scenarios are not to surface, but are to subsurface units. But yeah, I mean, our main remediation is to stop injection.
Yeah, of course.
And then the plume stabilizes very quickly, and there's no risk of further leakage.
Emma Cairns, Quintessa. From my experience, lots of oil and gas companies have been afraid to become part of decarbonisation for fear of failing financially, or it's just not part of their business plan. So how did EQUINOR initiate this sort of transition, and would EQUINOR be willing to share information on how to go about this with other companies that might be looking at doing this in the future?
On the last one, we have shared and we continue to share a lot of information. We have public release of data from Sleipner. We have shared it with many operators around the world as well. But on the first one, I have to give credit not to EQUINOR or Statoil, but to the Norwegian government, because the reason these projects go ahead is that there's a government framework for doing them. And I would say many oil and gas companies have shown willingness to do CCS, Shell, BP included, but without the framework and the support, they haven't progressed. So I hope my boss doesn't criticize me too much, but the reason why we've progressed in Norway is because of the public-private partnership and the regulatory framework. It's a desire both of the society and industry to have clean development. And Norway already leads the world on clean gas in the sense of gas flaring is almost prohibited in Norway. You have to have a very specific permit for gas flaring. And the Norwegian government with industry has been around the world to try and deploy gas flaring initiatives globally. And there's also a philosophy with the CCS part. We want that technology to be picked up globally.
Phil, we've talked quite a lot in the last couple of days about what things we need government to do. Could you tell us, sort of, not quite precisely, but with more detail, what do you need the government to do to get H21 going? What regulation is needed that it doesn't exist at the moment, please?
We have a whole commercial group on that, so I'm a little bit hesitant on it, but as I understand, there's a contract for difference for electricity, but not for gas at the moment. So we'd need some kind of, favourable terms for selling hydrogen into a gas market, okay? And we'd need some kind of assistance with the front-end design part. So there is a cash call that we're hoping that we'll get some kind of partnership between industry and government for the design phase of H21. But when you look at the long-term economics of H21, we expect that to be a fully commercial, self-sustaining project. But it's that transitional phase that's needed and that long-term commitment to the product in the market.
So it's not a regulation issue, it's a financial get over the hump.
It's a financial partnership issue, I would say.
Okay, just one more quick question, I think.
Actually, it's a comment. Luis von Boté from University of Geneva. As you know, I'm coming from the mining sector. And the influence of what is happening in Norway goes also to the mining sector, because, for example, in Norway, there's this sovereign fund, and it invests only in sustainable companies. So there is several companies that have shifted to transparency. So yesterday was the question how to advance in these questions. Transparency, trust, to be funded also by the Norwegian fund, which is the largest in the world.
I agree with you. You know, promoting transparency and democracy is very important.
Okay, thank you very much. So we'll move on.